In this video, we're going to talk about Vsepr, which is valence shell electron pair repulsion theory. It's better known nowadays as shapes of molecules in some specifications. What we're looking for you to get out of this session is being able to recall the names of the 8 different shapes which can be applied to simple molecules and ions. Be able to draw the different shapes of these simple molecules, ions, and to deduce the bond angles as well. So, what is Vsepr? Valence shell refers to outer shell electrons. So we're dealing with the outer shell electrons which are involved in the bonding. And this applies to molecules, only simple molecules. And so the main idea behind this is that pairs of electrons, whether they are bonding pairs of electrons or lone pairs of electrons, aka non-bonding pairs of electrons, all of these pairs of electrons will repel each other. And they repel each other to get as far apart as possible to minimize any of that repulsive forces between them. As I mentioned a moment ago, we have molecules which have lone pairs of electrons and molecules which don't have lone pairs of electrons. The lone pairs of electrons exert a greater repulsive force than bonding pairs of electrons. So we're going to look at molecules which have just bonding pairs of electrons first of all. This slide contains a lot of the information that you need to know. It shows you the number of bond pairs and also the shape which is associated with the number of bond pairs. Now the bond pairs we're talking about around a central atom. So an atom in the middle of your molecule, how many bonds come off it, or how many bonding pairs of electrons come off it. And as you can see, we've got, as the number of bond pairs increase, the bond angle decreases. And we're going to go through these examples now. So the first example is something like beryllium chloride. Beryllium, you're thinking, oh, it's a metal, but it tends to make covalent bonds rather than ionic bonds. Now, the main principle that we'll say over and over again is that the bonding pairs of electrons need to get as far apart as possible to minimize that repulsion. So in this molecule here, the way we can align the bonding pairs of electrons away from each other is by using by having this linear or this straight line shape. So we call the name of this shape is linear, and the chlorine beryllium chlorine bond angle is 180 degrees. And this applies to any molecule where you've got 2 bonding pairs around the central atom and 0 lone pairs. Okay, if we now add an extra atom, then this atom and these electron pairs coming in, so this electron pair with this new atom is now repelling those bonding pairs away. And so now we get a bond angle of 120 degrees. So you could apply this to something such as boron trichloride. So any molecule where the central atom is surrounded by 3 bonding pairs of electrons will have a bond angle of 120 degrees. So 3 bond pairs, no lone pairs, 120 degrees, and we call this trigonal planar. Planar refers to it being a two-dimensional object. So when you got two two bond pairs or 3 lone pairs, you have a two-dimensional object. Okay, so if we now go from 3 bond pairs to 4 bond pairs, now instinctively you might want to draw the 4 bond pairs in an arrangement like this. Oh. So just call it element X. And you'd instinctively want to put it in that kind of shape. But hopefully you can appreciate that this angle here that I'm drawing is just a right angle, and so that's only got a 90-degree angle there. Whereas if we go now to 3 dimensions, then we can get a larger bond angle of 109.5 degrees. You must remember the 0.5. It's not just 109, it's not 110, 109.5 degrees. We call this shape tetrahedral. So if we go back to the animation, you can see there that if you join the orange atoms together to make a face, then you get a shape with 4 faces, and the 4 sides are of equal size. The 4 sides are of equal size, and that is known as a tetrahedron. So, so when you have a molecule with 4 bond pairs, no lone pairs around that central atom, then you have a tetrahedral shape. When we go to 5 bond pairs, now this we will see in molecules such as molecules containing atoms such as phosphorus. Nitrogen doesn't form 5 covalent bonds usually or readily. Most of the questions you would encounter would be to do with phosphorus, or perhaps arsenic elements in group 5. When you have 5 bond pairs, no lone pairs, then you have a completely different shape. And the name of the shape is trigonal bipyramidal. Now, it's called bipyramidal because, well, the name trigonal. So you can see you've got this trigonal shape here, this trigonal planar shape here. But if you were to join the fluorines to make a face, just like we did in the animation on the previous slide for the tetrahedral shape, then you will form a pyramid on this side, and you would form a pyramid on the bottom side as well. So therefore, we call it trigonal bipyramidal. Now, if I just delete my ink, and then the bond angles. Now, these atoms here are sometimes referred to as being equatorial. These fluorines I'm just circling. It's called equatorial. And so the bond angle between these is 120 degrees. So that bond angle there will be 120 degrees, that bond angle there will be 120 degrees. The axial atoms, the ones above and below the plane of the equatorial, they have a 90-degree bond angle. So whilst you might think that having this fluorine perpendicular to this fluorine reduces the repulsion, in actual fact, because it's 90-degree bond angle, there's a greater amount of repulsion between this fluorine and this fluorine than there is between this fluorine and this fluorine. Finally, for the final shape with bond pairs only is called octahedral. We see this for atoms of We see this when we have sulfur as the central atom. Again, there are very few examples of the octahedral shape, because you can't have, say, SCl6, because the chlorine atoms are just too large to get 6 around the sulfur. The bond angle here is 90 degrees, so 90 degrees between the axial and the equatorial, and also here as well. That's 90 degrees as well. Okay, now irregular shapes, or shapes which contain lone pairs of electrons. Lone pairs of electrons, or we should really say lone pair repulsion, is greater than lone pair bond pair repulsion that we've got in the middle here, and that is greater than bond pair repulsion. So if we take ammonia for example, ammonia has got 3 bond pairs and 1 lone pair of electrons. If we look at the shape here, because we've got 3 bond pairs down here, and we've got a lone pair of electrons here being shown in the orbital here, it's kind of reminiscent of the tetrahedral shape we saw with methane before. But you cannot observe lone pairs of electrons. You can only observe atoms. And so whilst we can say we know these lone pairs are here, we can't actually physically observe them. And so this shape is now called pyramidal. It's called pyramidal rather than tetrahedral. Now, because of this increased repulsion between the lone pairs, so lone pair bond pair repulsion is greater than bond pair repulsion, this squeezes the bond angle here between the hydrogen bond angle is squeezed down, and it is reduced by about 2.5 degrees relative to the tetrahedral, and that gives us a bond angle of 107 degrees. When you have 2 bond pairs and 2 lone pairs around the central atom, such as molecules involving oxygen, we now have both lone pair repulsion and lone pair bond pair repulsion, in addition to the bond pair repulsion. So here we can see that we've got extra repulsion between the lone pairs. The lone pairs here. There's a bit of repulsion here, or extra repulsion between the lone pair and the bond pair there, and that's greater than the repulsion between the 2 bond pairs. So this reduces the bond angle even further to 104.5 degrees, and we call this V-shaped. Finally, if you've got a molecule with 4 bond pairs and 2 lone pairs, this is called square planar. The 2 lone pairs are axial, and here we've got a 90-degree bond angle. Thank you for watching.